Welcome back. So a while ago, we encountered a situation in which we had a triangle, and we had an angle, which we didn't know, but we had two side lengths. Maybe this side was 6 and this side is 12, and we wanted to find this angle. So we said, from this angle's perspective, we have opposite and hypotenuse, which means we can set up sine of theta equals 6 over 12. And this 6 over 12 is a number, right? This is going to become 0.5. And we said, sine of theta is a function. Perhaps we can consider an inverse function and say, maybe theta is equal to the sine inverse of the number 0.5. And we used the calculator to find that this was 30 degrees or pi over 6 radians. Right. And at the time, I said something like, we're just going to assume for now that this operation is valid and then investigate the details in the future. So that future is today. So let's begin the discussion today with a recap of the things we know about sine of theta. Namely, the graph of y equals sine of x and the behavior of sine within the unit circle. Okay, so we know that the maximum value of y equals sine of x is positive 1 and the minimum value is negative 1. And we know that it has a period of 2 pi, which means it repeats whatever one cycle every 2 pi along the x-axis. Right? So this positive 1 corresponds to the biggest possible value that sine of theta can have. In the unit circle, that would mean this one up here, because the y value in the unit circle cannot be greater than 1. Similarly, negative 1 is the lowest value we get on the graph, corresponding to the smallest y value we can get in the unit circle, which is negative 1. We say the range of the sine function is negative 1 to positive 1. Now, for the x here, this represents the angle. In the unit circle, we can have any positive angle by going around and around and around the unit circle, and we can have any negative angle by going around and around and around the unit circle clockwise. So we said the domain of the sine function is, sorry, not brackets, negative infinity to positive infinity, the entire set of real numbers. However, what if I were to ask the following question? Find theta such that sine of theta equals 1/2. So to understand what this statement means, I need to find an angle such that the y-coordinate in the unit circle is positive 1/2. So positive 1/2 right there. I need to find an angle where the y-coordinate is that value. Now, I have presented two possible candidates. I'll call this theta 1 and I'll call this theta 2. So it turns out we actually know these angles. We know that sine of pi over 6 is equal to 1/2. And we also know that sine of 5 pi over 6 equals 1/2. In this graph over here, that would mean I need to make the y value 1/2. So that point right there and that point right there. This is pi over 6, corresponding to the angle theta 1. And this, incidentally, is 5 pi over 6, corresponding to this angle theta 2. Okay, so we have information consistency. But perhaps you will remember the phrase one-to-one function in reference to functions having unique outputs. This is a case where the function does not have a unique or does not have unique outputs, because we have achieved the same output of 1/2 in multiple locations, meaning using multiple inputs, corresponding to the idea that every y value can be accessed multiple times on the unit circle, right? In fact, infinitely many times, because I can keep going to new periods. I can keep doing laps around the circle, which means if I were to try to ask the question here, what is the sine inverse of 1/2? perhaps I would encounter an ambiguity. Is the answer pi over 6? Is the answer 5 pi over 6? Is the answer something else? And that is not an ambiguity we're allowed to have with functions and inverse functions. So how do we deal with that? Domain restrictions, of course. So our goal in this domain restriction is to capture a segment of this graph. So we get all of the y values from -1 to +1 to preserve the range, but we don't let any y values occur twice, so we can stay 1 to 1. And there are many different ways we can do this, but we've all agreed as mathematicians to go with x equals -pi/2 up to x equals +pi/2 and capture this middle segment right here. So what that looks like is we can say f of x equals sine of x and hit control equals to bring up logical operators and say we want this to be -pi/2 and then hit control equals to bring up the logical operators less than or equal to x, once again, less than or equal to, and we're going to go with +pi/2. Hit this, and we get that segment right here. So we can see we have the range of -1 to +1, and it is 1 to 1. So the domain for a restricted sine function is going to be -pi/2 to +pi/2. And we accept that this is a general thing we all agree on. And for the range, we're going to end up with -1 to +1. Okay, so to get an inverse function, remember we switch the input and output, which means you're going to reflect this over the x equals y line. Here, we're going to say sine inverse of x and see what it looks like. Boom. So see, we've reflected over the y equals x line, and that's what we have. Now, the graph itself is probably less important than conceptually what we can say. We're going to say the inverse sine function. The domain and the range. So the domain of the original is going to become the range of the inverse because we're switching the input and output. And the range of the original is going to become the domain of the inverse. Okay. But what this means to us, when we do sine, the input of sine is going to be an angle in the unit circle. And as a result, we're going to get a y-coordinate, or in the case of a right triangle, opposite over hypotenuse. So if we switch the input and the output, what's going to happen is sine inverse of the y-coordinate is going to give us the angle. So to understand these restrictions, okay, the angle is going to be based on the domain here. So we're only allowing angles between -pi/2 and +pi/2. So in the unit circle, -pi/2 is clockwise down to here. And then +pi/2 is counterclockwise to there. So we're only allowing angles in the right half of the unit circle in the first quadrant and the fourth quadrant. Okay. And so, as a result, we can say that the range here, which is the y-coordinates, is going to become the domain of the inverse sine function. We are only allowed to put numbers in here that are between -1 and +1, because the y-coordinate in the unit circle can only be between -1 and +1. But as a result of our restriction, sine inverse will only give us angles that are in those two quadrants, which means now, if I were to say sine inverse of 1/2, which means go and find me the angle where the y-coordinate is 1/2. So if I go here and say, okay, the y-coordinate is 1/2, I can only access angles in the right half of the unit circle. So I know that that angle right there, which is pi/6, is the only choice I have. The answer here will become pi/6, no ambiguity. And let's check this in a calculator. If I go new page, add calculator, and I'm going to type in sine inverse of 1/2. I'm in radian mode, and when I hit enter, it gives me pi/6. If you don't have a CAS, you'll get this value, but you can quickly confirm that pi over 6 is the same thing. For sine inverse x, we put appropriate restrictions so that we would get a range on the inverse function of negative pi over 2 to positive pi over 2, including the endpoints, which means we're only going to get angles from down here to up here, all on the right half of the unit circle. Now for cosine, we're going to look at the graph of cosine x and place a similar kind of restriction where we want the y values from -1 to +1 with no repeats. And so the way we accomplish this is to cut it from x equals 0 to x equals pi, like this. Okay, so that means for cosine inverse of x, we're going to end up with a domain which is going to be based on the range of the original function. So that's going to be from -1 to +1. And then the range is going to be from 0 to pi, which is going to be based on the domain that we've restricted on our original function. So from 0 to pi means from here all the way over to pi. That is the top half of the unit circle. Now, what about for tangent? So with this graph, we want to restrict it so that we have no duplicate y values. And so we've chosen from negative pi over 2 to positive pi over 2 right there. And that gives us this. So the slight difference with tangent inverse of x is when we look at the domain of the inverse function, that's going to be based on the range of the original function. The range of tangent is actually all real numbers. So the domain of tangent inverse is going to be all real numbers. Then the range of tangent inverse is going to be based on the domain of the original tangent. So in this case, remember that there are vertical asymptotes here at x equals negative pi over 2 and at x equals positive pi over 2. So x cannot actually equal the endpoints. So the range here is going to be from negative pi over 2 to positive pi over 2 without including the endpoints. So this is once again the right half of the unit circle. So it turns out that for sine inverse and tangent inverse of x, we're going to consider just angles in the right half of the unit circle. And then for cosine inverse of x, we're going to consider just angles on the top half of the unit circle. This is going to be very important. Now, just for the sake of completeness, there are cosecant inverse of x, secant inverse of x, and cotangent inverse of x. And if you must know, the way we restrict these is we put cosecant inverse x on the right half of the unit circle, and we put secant inverse of x and cotangent inverse of x on the top half of the unit circle. But it turns out the way we do math, we can do everything we need to do with these three inverse functions and never touch these three. So I'm not going to discuss these explicitly because I would like to keep things a little bit more simple. Now, there's one more thing I need to tell you before we move forward. It turns out there are two different notations we use interchangeably for inverse trig functions, and they are the following. If I write sine inverse of x, this is the same thing as arc sine of x. And similarly, cosine inverse of x is the same thing as arc cosine of x. And tangent inverse of x is the same thing as arc tan of x. There's sort of historical reasons why we use these, and there's sort of geographic differences in what people prefer. You'll see me use them interchangeably, but I tend to write these for the Precalculus course. So let us now evaluate some things. First, I would like to evaluate sine inverse of root 3 over 2. So what this means, in the parentheses here, so I'm dealing with the sine inverse, this needs to be the y-coordinate in the unit circle, and I'm looking for an angle as my answer. So I can quickly sketch a crude unit circle and think to myself, where is the y-coordinate going to be root 3 over 2? Well, that's going to be up here. There are many possible locations where that can happen, but I'm only interested in the one that occurs on the right half of the unit circle. This angle, we know from previous experience, is pi over 3. So we can immediately answer pi over 3. What if we want to know cosine inverse of, and we'll go with a negative this time, negative root 2 over 2. Well, this thing in the parentheses right here, this is going to be the x-coordinate in the unit circle, because we're dealing with cosine inverse. So once again, quickly sketching a crude unit circle, we know that we want the x-coordinate to be negative root 2 over 2. And that happens in many locations, but we're only interested in the top half of the unit circle. So there's an angle right there, boom. And this angle, we know from experience, is 3 pi over 4. So this answer is 3 pi over 4. Now, hopefully you notice something. When I say from experience, this requires us to be very familiar with the special right triangles, the 30-60-90s and the 45-45-90s, and how they appear in the unit circle. So if there were ever a time for you to have those special angles and their x and y coordinates memorized, now is that time. So now I'm going to change the verb from evaluate to consider. Okay. And let's imagine I want the sine inverse of negative 1/3, or perhaps the tangent inverse of 2. So let's think about what these mean. This is going to be the y-coordinate in the unit circle. So if I do a quick sketch, I need the y value to be about negative 1/3. I should say exactly negative 1/3. So I don't need to be over here because I can only get an angle on the right half of the unit circle. So I know my answer is going to be that angle right there. Okay. Now, this angle does not correspond to our 30-60-90 or 45-45-90 special triangles. It turns out there isn't an easy way to write down this value at this stage in our lives. So this angle right here, we can write as sine inverse of negative 1/3. And we can put this into a calculator, and I can say, hit the trig button, hit sine inverse, type in negative 1/3, and hit enter. This is approximately negative 0.3398, rounding to 4 decimal places by value, but this is not exact. And so in the future when we're solving problems and I ask you for an exact value, I actually need you to write down this expression as is without putting down a number. And in fact, in the CAS version of the calculator, if I were to type this in and not hit approximately equal and just hit enter, it just tells me this thing. And it turns out there's a relationship between sine inverse of negative 1/3 and the sine inverse of 1/3 that we will investigate in the future. But do note that this is an exact value, and at this stage there isn't an easier way to write this. We just have to deal with it. The same kind of thing happens with the tangent inverse of 2. So this 2 is going to be the output of the tangent function, which is sine over cosine, which we can think of as the slope in the unit circle. So quickly sketching a unit circle, we want a location where the slope is 2. But since it's tangent inverse, we're only getting angles on the right half of the unit circle. So the slope of 2 would occur somewhere up here. This is the angle we're interested in. But once again, this angle doesn't correspond to the special triangles that we know. So this is simply tangent inverse of 2, and that's what I need you to write if you give me an exact value. We can approximate this by taking trig tangent inverse of 2, hitting Control Enter to get an approximate value. So sure, this is approximately 1.1071, but that is not an exact value. This is the exact value. So the last thing I want to discuss today is the idea of composing trig functions and their inverses. So I would like to evaluate the following expression. Sine inverse of sine 2 pi over 3. Now, to understand this, we say that sine of 2 pi over 3 is going to produce an output that's a y-coordinate. And sine inverse is going to take that y-coordinate and produce an angle. So perhaps naively, I might be led to believe that sine and sine inverse are going to cancel each other out and just give me 2 pi over 3 as an answer. But it turns out this is not the case, because when we defined the inverse functions for trig, we put some restrictions in place. So when we analyze anything of this nature, we have to be very careful. And by careful, I mean we should draw the unit circle and think about it before jumping. So sine of 2 pi over 3 means use 2 pi over 3 as the angle at the beginning. So if I go 2 pi over 3, then I will end up somewhere here, and I will have a y-coordinate. Now, it turns out that we know that y-coordinate, it's actually root 3 over 2, but we don't actually need to know that to do this problem, okay? Because what I know is I need to sine inverse of this specific y-coordinate, which means I have to go and find an angle that has this y-coordinate, but my angle has to be in the right half of the unit circle, which actually means I need to take this angle. That is the answer. Okay, but in order to reason through this, we say, oh, but in order to have the same y-coordinate, this triangle and this triangle are the same as each other, which means if I can find my reference angle right there, then I would use that to know my answer right there. Those two angles should be the same thing. So to get my reference angle, I would say, oh, well, pi subtract 2 pi over 3. The leftover in here, the reference angle is pi over 3. So I would happily conclude that my answer is pi over 3. Right? We can confirm this in a calculator. We can say, what if I go trig sine inverse of trig sine, and I'll go 2 times pi over 3, and we hit enter. See, we get pi over 3. This feels a little bit complicated at first, but it turns out you can systematically think through any problem like this and get the correct answer consistently. Now, using a similar kind of logic, we can actually solve a much more interesting type of problem. I would like to evaluate the secant of sine inverse of 1/4. Okay, so the first thing we do, we analyze from the inside, what is sine inverse of 1/4? Well, first of all, it turns out this we can think of as the y-coordinate in the unit circle. And that means this is going to give us an angle. And then we want to take the secant of that angle. Okay, so immediately, let's imagine we went through this and we said, okay, I need my y-coordinate to be 1/4, somewhere over here. I need to be in the right half of the unit circle. So I have this right there, and I have this angle. So why don't I call this angle theta for now? I would like to take secant of that angle, which is the reciprocal of cosine of that angle. Oh, I see. So what I'm supposed to do is I'm supposed to take this and say this is a value which I don't know. Why don't I call this k for the time being? And the y-coordinate is 1/4. Okay. And I'm looking to find, I can write this as 1 over cosine of the angle theta, which in our context is going to be 1 over k. So I need to find k. Well, in order to find k, I remember that this is a unit circle and the hypotenuse is 1. So by the Pythagorean theorem, I can say that k squared plus 1/4 squared equals 1 squared, or just 1. So I say k squared plus 1 over 16 is equal to 1, k squared is equal to 15 over 16, and when I square root both sides, I will get plus or minus the square root of 15 all over 4, but knowing that I'm in the first quadrant here, I would accept the positive value only, and that would be k. So my final answer would be the reciprocal of this, which is 4 over root 15, and I can rationalize to this value. So let's think about that real quick. What did I just do? I took this, and using the definitions of sine inverse and secant, I assigned meaning to this expression in the context of the unit circle. I said that very inside, this is the y-coordinate. Sine inverse gives me an angle as a result. So I'm just going to call this angle theta as a placeholder. Once I get that angle, I'm supposed to do 1 over cosine of that angle. So in the unit circle, I say the y-coordinate has to be 1/4. My goal is to find cosine of theta. Notice how I never actually had to find the angle itself. But once I find cosine theta, I can compute the final result. Now let's ask the calculator what it thinks the answer is. So we'll type in trig secant of trig sine inverse of 1/4. That's the approximate value, and this indeed is the exact value. All right, 2 more and we'll call it a day. First, we would like to evaluate cosine inverse of tangent of pi over 3. Okay, so first things first, we look at the very inside. This is the input for the tangent function. So this is going to be an angle. And then the tangent is going to give us the y over x in the unit circle, or as I like to call it, the slope. Okay, slope in unit circle. So if we quickly sketch out one of these unit circles, and we say pi over 3 is the angle, that's one of our special angles. We know the x and y coordinates of that to be 1/2 and root 3 over 2, which means the tangent of pi over 3 is y over x, which is rise over run. That is going to be root 3. So this can be resolved to the value square root 3. Okay. So now this is supposed to be the input for the cosine inverse function, which means this value is supposed to represent the x coordinate in the unit circle. However, square root of 3 is a number that's bigger than 1. Specifically, this is 1.7320508, and so on. Okay. The x coordinate in the unit circle cannot be bigger than 1 or less than -1. We have to stop there, which means this is out of the domain of the cosine inverse, which means this does not exist, and we cannot evaluate it. So with inverse trig functions, it's very important to be conscious of the domain whenever you perform calculations. So now, for the last example, I want to evaluate cosine of tangent inverse of 2 root 2. Okay. So this right here is the input for the tangent inverse function. So this is going to need to be the slope in the unit circle. Okay, so if I were to take this strictly from the unit circle perspective, and I say, I need my slope to be that number. That's a positive number, and I need to be in the right half of the unit circle. So perhaps there is some angle up here where that is tangent inverse of 2 root 2. Now, of course, I could make a triangle out of this and do the math that way. But it turns out it's conceptually easier to step out of the unit circle and to just draw a right triangle and to say, this angle right here, why don't we call this angle theta? So if I draw a triangle with an angle theta and a right triangle, then in the context of this right triangle, tangent of theta is the same thing as opposite over adjacent. That's the y over x in the unit circle, which means I can assign the side lengths here as 2 root 2 and 1. And I would successfully say that tangent of theta equals 2 root 2 over 1, which is the same thing as the tangent inverse of 2 root 2. Okay. From here, it is my goal to find the cosine of the angle theta, which means in this triangle, adjacent over hypotenuse. So to find the hypotenuse, I can just call this c, and then do 1 squared plus 2 root 2 squared is equal to c squared. That's 1 plus, that will be 8. So 9 equals c squared. And I'm going to take the positive, right, because I can put plus or minus, but really accept the positive one, because the hypotenuse has to be a positive length. So once I have c equals 3, I would have cosine of theta is adjacent over hypotenuse. And this is the answer. And of course, we can confirm in a calculator that if I take cosine of tangent inverse of 2 times the square root of 2, and then hit first approximate, so that's the value, and we know that value, but if I hit exact, I get 1/3. So in all of these problems, right, it's very important to remember what each function is doing. What does its input mean? What does its output mean? Because this is what's going to help you visualize and then decide what the most efficient way to handle it is. In some cases, it's drawing a unit circle and dealing with the x and y coordinates. In some cases, it's doing a right triangle and then doing SOHCAHTOA. Keeping in mind that these two methods are interchangeable as long as your angle is between 0 and 90 degrees, so you're in the first quadrant. And if you're not, you might have to do a little bit of clever going back and forth between quadrants, but the geometric logic ultimately prevails. So once again, this is the kind of unit where you just have to practice to get a hang of it. So with these things, especially with compositions of trig functions and their inverses, do a lot of practice problems. And the more you do, the more you'll start to see trends, and the easier every problem will become. Good luck, and please study hard. Take care.